Okay, meeting is now streaming live on YouTube, so we are on YouTube. So, okay. So I believe we can start. We are on the hour. So I'd like to introduce you myself. I did my PhD at the University of Lisbon, where I still work. I work on offshore structures, and I'll be chairing the renewable energy session for you today with my colleague Elif Oguz. She's an associated professor at the Middle East Technical University. We both work on offshore structures, and this is a new topic with many other things that are in renewable energy that the world is going towards these days. I hope it will be a fruitful and interesting presentation for you. All presentations will be that way. And I'd like to do the first presentation myself. This is our first paper. We are going to be presenting with Elif Oguz. So without further stopping, let's go ahead and start the process. Elif, would you like to say a few words yourself?
Yeah, I would like to say just welcome to our conference. It's very enjoyable, and I hope that everyone enjoys the rest of the conference.
Okay, is my screen share working? Can you confirm, please?
Yes, it works.
Okay, so let's start this session by giving an overview of platform types used in floating wind energy before we go on to others. This is a new topic. There is recently a lot of more people working on it, but a few years ago there were less. So this is going to be short, just to give you some brief information. Let's take a look at offshore wind energy, what is going on there. Offshore wind is recently picking up pace. When you look at installations of offshore wind, in 2013, the average depth was 16 meters. In 2019, it's now 33 meters. So the average depth of installations doubled in this time. Distance to shore is quite similar. It was 29 meters from the shore, now it's 59 meters. So the distance is doubled. This trend is supposed to continue. This is what we are expecting. So we are interested in reaching deeper waters with floating wind. So how can we do that? Up to 40 meters, what we can do is to use fixed bottom platforms. When you look at fixed bottom platforms, you see that they are actually installed, and up to 96% of them are actually installed in waters up to 40 meters. When you go past 40 meters, there's only 4% of the installations. Why is this? This is because it becomes not economical to go past 40 meters with fixed bottom platforms. When you go past this number, what you start considering is floating platforms. There are basically four types of them. One is the barge, the other one is the spar, there's the tension leg platform, and there's the semi-submersible. Just by looking at them, they might be a bit difficult to understand, but it is possible to classify them. So here are some examples. There are three semi-submersibles that you see on top that are slightly different from each other. The first one is quite different than the others. And there are three tension leg platforms on the bottom, again, different hull forms. So you can expect to see quite a lot of differences in terms of geometry. But when you want to classify them, you can classify them by relying on their stabilization methods. This is a triangle that represents the three options that you have. One is ballast stabilized platforms, the other one is buoyancy stabilized platforms, and the third one is mooring stabilized platforms. In reality, all of them use a combination of these methods, but they rely primarily on one of the options. So this is an older work coming from 2007, and I believe it can be extended slightly further. It can be detailed a bit further. Let's take a look at every single one of these options. So imagine that you have this structure on the left that you see in the picture, and you want to stabilize them using ballast. So you're going to add some weight to make this turbine stable. Where would you add it? If I asked you, you intuitively know that you're not going to add it on top. You're going to add some weight deep down somewhere so that it balances out with the turbine on top. So this is the principle of ballast stabilization. You add ballast deep in the structure, deep in the hull, to stabilize your platform. SPAR is exactly this type of a platform. You see an example on the left. This is an abbreviation, SPAR, single point anchor reservoir. And it is a deep ballast stabilized platform. The idea is to add ballast deep in the structure to serve as a countering moment. Then what is called the buoyancy stabilized platform, but it isn't that descriptive. If you think about it, all platforms or all floating structures have buoyancy applied on them. So why does it stabilize one and doesn't stabilize the other? The idea there is the distribution of buoyancy, and a good reference to it, a good way of saying it is water plane area stabilization, because the water plane area gives you an idea on how the buoyancy is going to be distributed. So this is the principle of the barge. You see it there on the left side. It is a shallower draft, larger water plane area, and this is how it is stabilized. So the barge is that type of a platform. And there's what is called the mooring stabilized platforms. Once again, the same description. These three platforms on the left, TLP, semi-submersible, and spar, they all have their moorings. So why does it stabilize one and doesn't stabilize the other? What actually stabilizes a tension leg platform is actually the excess buoyancy. You have a large buoyancy and a smaller mass. So what ends up happening is that you are actually pinning the structure upwards, creating some tension in the moorings, and this tension is what is stabilizing your structure. So basically, buoyancy is acting as the stabilizer here by having excess buoyancy. We can call these structures tension leg. These structures are called tension leg platforms, and they can be referred to as tension stabilized platforms. Here's an example, so we can place it there. And there's finally the semi-submersible. This is a work from 2014, for example, trying to classify the semi-submersible. You can see that it has been placed somewhere between buoyancy and mooring stabilized. But let's take a look at a real design, an existing design. This is the OC for semi-submersible that you see on the left. It has 4 tons of steel and 10 tons of ballast. So apparently it does rely on ballast. It is 2.5 times the mass of the hull structure. So it also depends on water plane area, because it has these 3 columns that are distant from each other. So you have the water plane area, the restoring coming from there, plus slightly deeper ballast, which ends up describing the semi-submersible. DNV classifies them as column stabilized structures. This is where you should find your semi-submersible, somewhere between ballast and buoyancy stabilized. Okay, so let's rename this triangle. We can practically call it this way. There are deep ballast stabilized structures like the spar. There are water plane area stabilized structures like the barge. There are tension stabilized structures like the tension leg platform. And there are semi-submersibles which are stabilized somewhere between water plane area and deep ballast. Using these principles, we try to design platforms, and these are our goals for wind. We are interested in easier production because they are going to be installed in larger numbers. Again, the same principle leads to smaller hulls because you don't have a very large payload. Unlike oil and gas, you can have one platform that produces for 20 years, billions of euros. That's not the case. You're going to have to design and install maybe 50, 60, maybe 100 structures. So you're interested in smaller hulls. Minimal effect on turbine dynamics is another concern. If you start to have pitching, then you start to affect the aerodynamics of the turbine. That is not something that you want. You would like to keep the motions limited. Easy transport and installation for the same reasons that I've given, and then easier decommissioning after the end of life, which is 20 years. When it comes to the dynamics, it is the same, the equation of motion. You have the forces, aerodynamics and hydrodynamics. Aerodynamics is significant. You have the mass matrix, you have the hydrodynamic coefficients, added mass and damping, and then you have the restoring forces from hydrostatics and the mooring. So when you have an idea, you go ahead and to solve it for mass, then we either use panel codes or, if applicable, usually it isn't, the Morrison equation to solve for hydrodynamic coefficients. Then hydrostatics is very similar to ships. That is where we get it from. Mooring can be calculated using specialized costs, specialized methods, or in the worst case scenario, you can just do a stiffness matrix, add it that way. And you know which turbine you're designing for, so the forces are coming from there. When you look at the dynamics of these structures, they are mostly compliant structures, which means that when you have a force in a certain direction, let's say surge, the structure complies by moving in that direction. There's only one structure that is a bit specific here, that is the tension leg platform. It has two modes that are called restricted modes, which means that motions in those modes are rather small. For example, the heaving and pitching of a tension leg platform that is 50 meters will not surpass 10 meters of heave and maybe a single unit degree of pitching and rolling. These motion specifications also play a role in their resonance characteristics. Normally, when we are trying to design offshore platforms, what we try to avoid is the wave range, and DNV gives it as 5 to 25 seconds of wave excitation frequency ranges. If a structure is restricted in some modes, you try to stay below this, so 2-3 seconds of frequency, almost like a rigid structure. And if it's compliant, then you try to go about 25 seconds of wave frequency to make sure that natural frequency to stop the structure from getting into resonance. So these are the main principles behind offshore platforms. From here on, I would like to leave the word to my co-chair, Elif Oguz, to say a few words on the state of the installations in Europe. How are we progressing in this manner? So Elif, it's all yours.
Okay, thank you very much, Emre. I would like to just finalize the presentation by mentioning the recent report, which is published by Wind Europe recently. In 2020, 14.7 gigawatt of new wind capacity were installed in Europe, as you see here. Actually, this was 6% less than in 2019. And it was 19% less than what the Wind Europe was expected before the COVID situation. And when we have a look at this plot, actually we can realize 80% of the new installations were in onshore. And the Netherlands here had 2 gigawatt of installations. Actually, it was the most wind capacity in 2020, having most of it in offshore. And as you see here, Norway installed a record of 1.5 gigawatts of wind capacity, and all of it in onshore, as you see. Germany, on the other hand, shows the lowest rate of installations since 2010, but onshore installations increased slightly to 1.4 gigawatts due to small improvements in permitting rules. Now I would like to finally mention about the Turkey situation, what is going on in Turkey. Turkey has 1.2 gigawatts installations in 2020, which is equal to 8% of installations in Europe. Actually, wind installations in the first half of the year were severely impacted by the international travel ban, but the developers in Turkey managed to obtain a 6-month extension on the commissioning deadlines of the wind farms with support of the awards which was obtained in 2018. And in the last slides, I would like to just show you the total wind installations in Europe, the current situation. As you see here, 220 gigawatts of total installations we have in Europe, and only 11% of it is in offshore. But still, of course, we all will be working on offshore part. I would like to thank you, and if you have any questions, we would like to happy to answer. Thank you.